Okay, so welcome back. So I hope you remember what we were doing last. What were you doing last before the break? Something. Speak up. Speak up. Been a while. Even I forgot. Tell me what you were doing last. Constant current source bias, and we are trying to make common source amplifier with the constant current source bias, right? So we saw a couple of architectures, and one of the architectures that we were discussing before we stopped was this, in which the constant current source was, firstly, I mean, you need the resistor at the drain because it's a common source amplifier, otherwise you will not get any amplification. And we were sticking a current source at the source, and at the input side, obviously, you have, at the gate, you have the bias plus the input. And then we saw that if we only keep it like this, right? If we only keep it like this, what will be the incremental current? What will be the incremental current through the transistor? Zero, right? It's a constant current source, which by definition means that current cannot increase. So incremental current is zero. So if we take the output from the drain of M1, so it will be zero. So this is by no means a common source amplifier. Then we saw that the reason behind it being zero was the source was following the gate, right? Because it's a constant current source bias. So the voltage at the source would have followed the voltage at the gate, so that VGS becomes always zero. Since VGS is not allowed to change, you cannot have incremental current. And so you cannot have incremental current, there is no way you are going to get incremental voltage, right? So then we devised a strategy. What was the strategy? I mean, this architecture biases the transistor using constant current source. So all the good things of constant current source bias come in. That is, the GM doesn't change with threshold voltage, it is less sensitive to mobility and so on. But it doesn't give amplification. It doesn't give amplification because the source is now changing with the gate. Source is not fixed. Source is not incrementally grounded. So we needed to incrementally ground that. So we put a capacitor here, right? So let's call it C infinity. So this is, if the capacitor is infinitely large, then for any non-zero frequency, it will behave like a short circuit, right? And then you will have an incremental current, right? The incremental current will then flow through this path, and the bias current, that is the DC current, will flow through this path, right? So if that is the case, then it kind of satisfies both the conditions of the transistor being biased using a constant current source, while the incremental current is getting a path to flow through the capacitor, right? So which means the source is moving along with the input voltage as long as the input voltage is DC, but the source is incrementally grounded for any non-DC input. Okay, so essentially that's why it's a common source amplifier, or a common grounded source amplifier for any non-zero frequency inputs. Okay, fine. Yeah. So I'm sure you have seen this circuit multiple times in different contexts, but this is basically a spin on this. So now the question is, the C infinity you cannot ever get, right? So what is the size of the capacitor? What is the minimum size of the capacitor that is required to ensure that at certain signal frequency omega naught, right? So this is, let's say, V naught, Vi is at omega naught. The capacitor C infinity behaves like an infinite capacitor. Okay, so I need to find that. So what should I do? So what I'm asking is what is the limit of C infinity? You are making something on the breadboard. You cannot put an infinite capacitor. You have to put a finite value of the capacitor. So given that your signal frequency is at omega naught, what is the minimum value of omega naught, or what is the constant on omega naught, or what is the constant of C infinity that you need to ensure, so that at those frequencies of omega naught, the capacitor acts as a short circuit? So what should I do? Yes. So what will be that equivalent R?
What we are seeing at the moment.
Right. So I have to Thévenize the circuit. Whatever capacitor is seeing, I have to find out the Thevenin equivalent resistance looking this side. Right. So you can assume that you have a box. Inside the box, you have a capacitor. But I'm trying to figure out what is the Thevenin equivalent resistance looking here, right? What is the RTH? If I know this RTH, then I know what is the value of this capacitor that is required. So what is the RTH? Calculator, tell me what will be the RTH. By the way, all these are in incremental sense, right? So even though I have placed the transistor, we are all doing incremental calculations. So what is RTH? Okay, fine. So quickly, so if I replace the incremental model of the transistor, so this is what we are supposed to get. Input will be shorted. Apply V test here, and you have this. This is anyway shorted, and this will be GM times minus V test. So the current that you are drawing, that is I test, is GM times V test in the direction shown. So RTH is 1 over GM. Okay. So you know RTH. So what is the constant on C infinity? C infinity should be much greater than what? 1 by omega naught RTH, which means this is 1 over GM, right? So basically GM by omega naught. Okay. So as long as you can satisfy this criteria, you are good, right? So for these, this will behave like a common source amplifier for frequencies of higher than omega naught or lesser than omega naught. So let's say you find out this value at 1 megahertz. Let's say you require 1 nanofarad capacitance. Then will this common source amplifier behave like a common source amplifier for higher than 1 megahertz or lower than 1 megahertz? So higher than 1 megaradian per second or lower than 1 megaradian? Lower. Why? Lower? What is low first? So what happens at lower frequency? Does the capacitor behave like a short or does it behave like an open? Lower frequencies. Open, right? We want this constant is for capacitor to behave like a short circuit. So if it's short circuit at, let's say, 1 megaradian, then it will be a better short circuit at lower frequency or a worse short circuit? It will be worse, right? I mean, lower frequency goes towards the open circuit, right? So essentially, this will work properly for higher frequencies. So if, let's say, you have a band of frequencies for which you have to satisfy your criteria, right? You know that your, let's say, the band for which, frequency band for which the common source amplifier is supposed to work is from, let's say, 10 megahertz to 100 megahertz. So for which number, 10 or 100, are you going to fix the C infinity? 10. 10. Why 10? At 10 megahertz, then right. Right, exactly, right? If it's a short at 10 megahertz, then definitely it's a short at 100 also, right? So we start off with the worst case condition. Okay, fine. So now let's. This is what essentially a common. I mean, there are many ways, many other ways you can make a common source amplifier with different types of biasing. We have discussed one in the previous lecture, and this is the one which we started discussing before we stopped. So let's use the same architecture and try to see if we can make something different. Not a common source amplifier. Let's see if we can make something different, right? So we'll keep the same bias. So for the biasing picture, I don't need this resistance. So let's forget about the resistance. And we also saw that if this is Vs, right? So what is Vs over Vi? Or rather, what is Vs with respect to Vi incrementally? Same, right? So current cannot change. So if Vi changes, Vs also has to change accordingly, because VGS has to be incremental VGS has to be 0, right? Or the total VGS has to be constant. Okay, fine. So this is kind of a source follower, right? So that's this is a source follower architecture that we have studied before the midterm break. But now, if I say that, what happens? So currently, it's not driving any load, right? It seems like the output and the input are separated from each other, but the output is not driving any load. So what if I attach a load to Vs? Will it still be a source follower? That's the question, right? So what I'm essentially asking is, let's say I have a load resistance RL, right? And let's say I simply connect these two, right? So firstly, what's going to happen if I simply connect these two to the biasing picture? Will the biasing picture change? It will change, right? Because now the current I0, which was getting pulled through M1, is getting divided between the transistor and the RL. Or in other words, if I connect it like this, do you think the transistor will push out more current than I0 or less current than I0? More current, right? Because now the transistor has to support two. It has to support both the current source and the current that will go through RL. Right? So essentially, transistor is going to sink in more current, right? Or rather push in more current. So that changes the biasing picture. If I don't want to suppress, if I don't want to change the biasing picture, what should I do? I still want to connect RL. Capacitor, right? I can put where should I put the capacitor? Right. Oh, good. So I can connect it here. I can put a capacitor here. Let me call it C infinity. Okay. Fine. So I connected it here. So now DC picture doesn't change. All good. But now what I'm asking is that if this is, let's say, I call this V0 now. Okay. So we know that for this is we know that for RL equal to infinity, V0 is equal to Vi. This we already know, right? We have argued, we have done the calculations, everything multiple times. So this we already know. What I'm asking is, will V0 be equal to Vi for RL not equal to infinity? Approximately. Obviously, it will not be exactly approximately equal to Vi. But let me just, instead of will, let me ask can. Can V not be equal to, approximately equal to Vi for RL not equal to infinity? What I'm essentially asking is there any range of values of RL for which V naught will be still be equal to Vi? Yes or no? Yes. Okay. So why do you, anybody who says no? What about you guys? Is the question clear? What is the question? Yeah. Is it possible to get V naught equal to Vi for some range of RL? I heard somebody say yes. I'll come back to yes, but let me ask whoever is saying no. How many of you are saying no? Yeah. Why no? Right. Exactly. Right. Yeah. Right. Go ahead. Yeah. You are right. On the right track. Yes.
So the output will change because of
Yes, correct. Right. So that's why I'm not saying exactly, I'm saying approximate. Right? It cannot ever be equal. It cannot ever be equal because, as you rightly pointed out, if now in the incremental model, RL is going to draw some current. Correct? If RL draws current, your incremental VGS will not be zero anymore. If the incremental VGS is not zero, then obviously source and gate are not following each other. Right? You have to open up the VGS. So which means source cannot follow the gate fully. So it cannot ever be equal to 1. I agree. But can it be a case in which it is approximately equal to 1? If RL is very large, right? If RL is infinity, ideally. But when you say very large than what? Very large is a relative term. Huh? Why one was given? Yeah.
And calculated incremental gain.
Okay, you are calculating incremental gain. That's fine. But let's say this is not a common source amplifier, it's a complicated circuit, many more transistors and all. Then what is the one test that you are going to do is to ensure that this is equal to the incremental gain is same as when RL is equal to infinity. See, I'm not giving you the exact term. If I tell you the exact term, you will immediately say. You will definitely get the answer. Pardon? Right. So essentially the question that I'm asking without really using the technical term is RL loading? Is RL loading your structure? Right? RL equal to infinity means RL is not loading. I am asking, is there a range of RL for which it doesn't load? Right? So now you should be able to immediately say, when I'm asking if RL is loading or not, what are you going to test? Output resistance. Right? Remember that first or second assignment, a box, whether it acts as a voltage source, whether it acts as a current source. Right? So essentially whether you are getting, whether RL is loading your circuit. If RL is not loading, you will be getting as, your answer will be same as RL equal to infinity. If RL is loading, then it will be something different. Okay. So what is the incremental output impedance? Or rather, what is the impedance looking in? 1 over GM, right? We have done this. So essentially, the answer is yes, as long as RL is much greater than 1 over GM. Or GM RL is much greater than, right? For as long as GM RL is much greater than 1, or RL is greater than 1 over GM, or GM is much greater than 1 over RL, then you get this to behave like a source follower architecture, right? Or a voltage buffer, because ultimately it's buffering. RL is not, now essentially you are not loading RL with VS directly, right? So there is isolation between the input and the output is following the input for a range of values of RL, right? So this is essentially a voltage buffer, right? So there are several, we call this architecture using several names. One is obviously source follower that we talked about earlier. The second is voltage buffer. This is an unity gain buffer, kind of, because you cannot get gains of more than one. The third is, we also call this a common drain amplifier, even though it doesn't amplify. Right? Why common drain? Because the drain is incrementally grounded. Right? So it's common means grounded. So grounded drain amplifier, grounded drain structure, we call it common drain amplifier. Okay. So this is often used to buffer an input while driving a load. Right? So that you get at least a gain of unity, approximately a gain of unity. Okay. Make sense? Any questions? So now what I want you to do is to find out what will be exactly V0 over Vi. Right? Put pen to paper and tell me what will be the exact V0 over Vi for this architecture. Okay, so I see some of you have got it already. Some of you have replaced. I saw some mistakes, so let me address that first. So if I I saw some of you were sketching the incremental model like this. So is this correct or incorrect? But if I say that, I mean, my incremental equivalent of this is this correct or incorrect? Why incorrect? Right. So we need to identify what is the source and what is the load, right? So if you are not sure, so let me give you this strategy. If you are not sure, you should always do this. So where was it? Here, right? So don't try to replace everything at one shot using intuition if you are not sure about the details. If you are not sure about the details, just replace one element at a time and see what we end up with. So in this case, what will you replace? So let's start with the left-hand side. VI, incremental VI is shorted. Biasing is shorted. Then you go to the transistor. Transistor has 3 terminals: gate, source, drain. And you know the transistor, even before applying anything, you know this is the incremental model of the transistor. This is source, this is gate, this is drain. This incremental model of the transistor doesn't change just because you have put it in a circuit. This is always the same. Now, what is connected to the drain? In this case, the drain is incrementally grounded because it's VDD. So this goes short. What is connected to the source? You have a current source here. This current source goes off, not required. What is connected? What else? You have a capacitor, which I told is incrementally shorted. So that shorts. Then you have a resistor RL. And many of you are writing this as GM times VI. It's never GM times VI. That's an incorrect transistor equivalent. All right. So it's always GM times VGS. Right. So if you write GM times VI, we don't even proceed beyond that. That's a fundamental mistake. Okay, even if your answer is correct. So it's always GM times VGS. Now, in this case, what is VG? In this case, VG is, you have an incremental input here, right? You have an incremental input here. So gate voltage becomes VI. So VI, but source is not grounded. So it becomes minus VS. This becomes your incremental circuit. Then you solve for it, right? You solve for KCL at the source node, you will get the source voltage, right? Solving is the easiest thing to do. So once you solve it, what are you going to get? You are going to get V0 over Vi or Vs over Vi in this case. V0 over Vi will be equal to GMRL by 1 plus GMRL. I'm not doing the KCL solution. I'm sure all of you are expert in that. So this is what you are going to get. And you see that if you satisfy this condition, then you get V0 over Vi to be equal to the same as equivalent to RL tends to infinity. That is equal to 1. Okay. So oftentimes it's not possible to, if the circuit is slightly bigger, it's not possible to calculate exactly what is the V0 over Vi is or what is the transfer function is. In those cases, in order to figure out the loading, you just simply find out the output impedance. Okay. Okay, fine. Any questions? Okay, so let me ask you one more question before we move on. So again, we put this C infinity. So what is the limit on C infinity? How do I figure out what is, I know how to figure out. Now I am asking you what is the limit on C infinity so that C infinity acts as a short circuit at some frequency omega naught. Calculate and tell me. 1 by GM. Yeah. So it will be 1 over GM plus RL because you see this side we already figured out it's 1 over GM. On the other side, the capacitor has RL. So essentially, if I sit on the capacitor, right? If the capacitor is a black box, this side the resistance is 1 over GM, right? This we figured. Incrementally grounded. On other side, I have RL. So this is the loop. So the capacitor C is equivalent Thevenin impedance of 1 over GM plus RL. So C infinity has to be much greater than 1 over omega naught RL plus 1 over G. Okay, for it to behave like a short circuit. Okay. Yes.
Instead of increasing RL for unity gain, then increase GM.
Yeah. Good question. Sorry, I almost missed that part. Right. So sometimes what happens, I mean, not sometimes, almost always RL is not in your control. RL is some block that you are driving, right? So for a given value of RL, you have to make this look like a unity gain amplifier, right? So what you need to do, you have to set the value of GM. Right? You have to ensure that GM times RL, the new GM that is in your control, that times RL has to be much greater than 1. It is only then it is going to fall, it is going to act like a source follow. Right? So designer variable is GM. So then you do whatever is needed to increase the GM, right? You increase W by L, you increase I0, you do all sorts of things to increase the increase GM. Okay. Yeah, good question. Okay. So now let's move on. So all these things we were doing because we wanted an amplifier in negative feedback. Now we wanted the amplifier in negative feedback to have a stable GM, right? Because all the parameters were a function of GM, or strong functions of GM, especially unity gain frequency, phase margin, DC gain, everything is a function of GM. So we wanted an unity gain. We wanted an amplifier whose characteristics are incremental characteristics are independent of the ambient variation, like threshold voltage variation, and less dependent on the mobility variation. So that's why we were looking for architectures which can be biased using constant current source, because we saw that constant current source biases have these good things. Okay. So now if that is the case, so let's go back to our feedback model, right? So this was our generic feedback model, and you had an amplifier here. You have VI, V0, and you have a feedback wrapped around it. And as it turns out, and we have seen, you have seen in this feedback model in your UG courses also multiple times, but not in this format. As it turns out, this guy, I can, this entire stuff, I can break it up and say that this AV has two terminals. One is plus, one is minus. This goes here, and VI goes here. Okay. And you can call the terminal AB, doesn't matter. And often instead of making this a square, we represent it like this. Right? So this is the classical op-amp picture that all of you I'm sure, are familiar with. So now, so this, as you see, this op-amp picture is exactly similar to that of a feedback network that we have been using for a while. So now we also saw that a transistor, I mean, what is an op-amp? It amplifies the voltage difference between its two terminals, right? So if this terminal is VA, this terminal is VB, right? So AV is equal to output is equal to AV times VA minus VB. So it's a difference amplifier, right? It amplifies the difference. So in our case, a transistor also is a difference amplifier, right? So because a common source amplifier, or rather, I shouldn't say common source amplifier. So let's say I have a transistor. In the incremental model, if this is VG, this is VS, this current is GM times VG minus VS, right? So it's producing a current which is proportional to the difference of two voltages, right? And if I pass it through a resistor, it's going to produce a voltage which is GM times VG minus VS times RL, right? So this, which essentially means that if I connect incrementally, I mean, obviously I'm not showing biases here. If let's say this is VA, this is VB, right? Two voltage sources connected at VA and VB. So this is VA and this is VB. So V0 will be, V0 that is the drain voltage. V0 will be Gm times RL times VA minus VB. And if I say GMRL is equal to that AV, right? So this is like a difference amplifier also, right? So now the question is, can I use this difference amplifier directly in the way that I have shown in the negative feedback loop? If I can, why? If I cannot, why? That's the question.
There is an impedance mismatch.
Exactly, right? Very good. So there is an impedance mismatch, right? So in this block diagram of op-amp that we take for granted, the thing that we implicitly assume is the impedance here is infinity. Impedance looking into this terminal is also infinity, right? This block diagram essentially means that. But in this case, the impedance in one terminal is infinity, but the impedance in other terminal is 1 over Gm. Right? Do you agree? So if that is the case, this we cannot use as a difference amplifier because we don't have an ideal voltage source. If we had an ideal voltage source instead of VB, right? If we had an ideal voltage source, then I could have as well stuck that voltage source directly at the source without having any issue, right? But since you never have an ideal voltage source, which means moment you connect anything to the source, it is going to draw current, and that voltage source is going to have its own internal resistance. You are going to have a drop. So the source will not see exactly VB, right? Source will see a reduced value of VB, right? So transistor will load the source, in other words. Okay. So essentially what I am trying to say is, in principle, you are going to have an input VA with our internal resistance RA, let's say, and you are going to have another input VB with another internal resistance RB. And if you connect your transistors like this, incrementally, this node, so this node will be equal to VA, but this node, the source node, will be less than VB, right? So your transistor is not amplifying VA minus VB. Your transistor is amplifying something else. If you calculate, you will see that it's still proportional to VA minus VB, but not, it's not Gm times VA minus VB. Okay, so this is a problem.
But it will automatically drag to negative.
Okay, so it will, can you elaborate on that?
Negative feedback.
You mean if I put it here, if the negative feedback is used here? Yes, so it is going to make it equal as long as when AV is really high, right? So now in this case, what is AV? AV will be a function of RA and RB, rather in this case RB, right? Because this current is Gm times VA minus the source voltage Vs, right? And source voltage is not equal to VB. Do you agree? Source voltage is not equal to VB. It is smaller than VB, right? Since this is smaller than VB, you are not going to get this current equal to Gm times VA minus VB, which means your gain is dropping, right? Since your gain is dropping, you are going to have a problem. The bigger problem will be, you don't know whether what is the resistance RB in general, right? You can have a previous stage. You can have a previous stage which gives you a very high output resistance, right? For example, in this case, if in this case, this terminal VB is equivalent to the source terminal, right? So what is the output resistance? The output resistance will be this, right? K minus 1R, this R. So the impedance looking this side will be the output resistance of the previous case, kind of, right? Whatever is driving that node. What is driving the node? It is being driven by this resistor divider. So that can be, this can actually be very high, right? Because ultimately this resistor divider is being driven by your op amp or whatever amplifier. So you don't want this to load that op amp. So which means you ideally this has to be like infinitely large, very large. So if this becomes very large, will it be able to drive a source? Right? If the resistance so essentially this RB, if I call this one R1, we call this to R2, this RB is equal to R1 parallel R2. Right? Equivalent to this picture. If I look into the output resistance here and I assume V0 is shorted, then the impedance that it is seeing is R1 parallel R2, right? So if that is the case, which means that the source has to be driven by the transistor itself, right? So that's the problem. That is a big problem, which means that generally, in a generic sense, you will not be able to do this. I mean, you can always argue that if RB is very less than 1 over GM, there is no loading, but that's an additional constraint that is difficult to satisfy. Okay. So if we don't want this loading to play spoil sport, what are the other possible scenarios? How can we fix this? We still want to make that op amp, right? But we want this voltage to be, even that voltage to be that. I don't want this source to load the voltage source, right? So essentially what I'm asking is, I still want, there's no problem with this guy. VA is not getting loaded, but I have another source, VB, which is now getting loaded. Can I put something in between here so that it doesn't load VB? Capacitor in parallel with RB, right? So how will that help? A capacitor in parallel with RB. I just wanted to ask, why will capacitor in parallel to RB? Firstly, this RB is an internal resistance to VB. Right? So you don't have access to that. If I had access to the other terminal of VB, then I could have just connected that terminal, right? So we don't have access to this terminal of VB. So this is not possible. But yeah, so I heard one answer. Any other answers? Compound amplifier, right? I can put as source follower, right? The one that we just looked at. Right? So we can put that source follower. So this, let's say, is a compound amplifier. This is grounded. So what should I do? Incrementally, again, in the incremental sense, even though I'm drawing transistors, this is an incremental sense. So let me replace the transistor with this incremental sense so that it makes more sense. So let's say this is Vs. So this is GM1 times Va minus Vs. And I replace this guy with this incremental model. This is shorted. Let's say this is also Vs. Let's say VSB. So this is GM2 times VB minus VSB. So VSA. Okay. So what is the next thing? We wanted to ensure that the voltage VB appears at the source of the first transistor, right? We couldn't connect it directly because it was getting loaded using RB. So now we are trying to use a source follower or a component amplifier, a voltage buffer, you name it, all of them are same thing. So what we are planning to do, we are planning to connect these two, right? So essentially what we are planning to do is, so by the way, we have this resistance here anyways. So if I draw a cleaner picture, so this should look like this. So this is GM1 times VA minus VS. And since we're connecting these two, both BSs are same, this is grounded, and you have RB. So this is GM2 times VB minus VS, where this is the VS. Okay. So by the way, note that these sources are connected. I mean, these are shorted incrementally, and this is also shorted to that. Okay. So now can you tell me, so for the first, let's look at the first issue. The first issue is our transistor GM1 is not loading VB. So that issue is solved. But next the question is VS equal to VB? Right? That's what we wanted. Right. So how should I know what is VS in terms of VB? I can find out the KCL at the node VS, and then figure out, right, what is the impact of loading in this, right? So solve for KCL at VS, and let's see what we get. Yeah, good. I saw many of you have got it right. So so VS will be equal to GM1 VA plus GM2 VB by GM1 plus GM2. So if we are only considering the effect of VB, and we are trying to figure out whether what is VS in terms of VB, we can assume VA to be 0. So we can basically say that, I mean, you can do this analysis using superposition or using both the inputs simultaneously placed. If you use superposition, you are going to get this. For VA, you are going to get GM1 VA by GM1 plus GM2. For when VB is active, you should get GM2 VB by GM1 plus GM2. So this is the contribution of VB on VS, and this is the contribution of VA on VS. Okay. So as you can see, there is a division, right? It's not as if even though we used a voltage buffer, even though we use a common drain amplifier, entire VB is not coming to VS, right? So a fraction of VB is coming to VS, right? So why is a fraction of VB coming to VS? You can obviously say that, okay, algebra says so, but other way of thinking about it is, what is the impedance? What is the impedance that the source of the first transistor is seeing, right? So essentially what I'm asking is that this is your common drain amplifier. So what is the impedance that this guy is seeing? 1 over GM1, right? So the RTA that it's seeing is 1 over GM1. And what was the constraint? The constraint was, if this has to behave like a common drain amplifier, what was the constraint? The constraint was this resistance has to be much greater than 1 over GM2. Right? So if you impose the constraint of 1 over GM1 to be much greater than 1 over GM2, right? So what are you going to get? You are going to get the second term to be unity, right? So one might say that I can obviously choose the value of GM2 to be much greater than GM1. If I choose the value of GM2 to be much greater than GM1, then VS would be equal to VB, then we are all good. Right? So that is a possible scenario. You can design like that, right? So that definitely is possible. You can design like that. That will be one type of solution. But in case of an op amp, right, since we are trying to get an op amp into our picture, so what, as it turns out, one of the requirements for the op amp is both the terminals are identical, right? So not only that input impedances are identical, you might want to connect the input here, or you might want to connect the input there, or you might want to swap places also, right? So essentially, what that boils down to is symmetry. We want, in more cases than more often than not, we would want the two transistors, the two incremental transistors, to behave like they are identical, which means that we want both the GMs to be identical. Now, if both GMs are identical, then obviously one cannot be much higher than other. So you live with this voltage division. If the GMs are identical, then you get VA plus VB over 2. Like both, I mean, the second transistor is loading the first transistor is loading the second one. But the good thing is that this loading is a function of its own transconductance. This loading is not a function of the internal resistance of the sources, right? So this is not dependent on RA or RB, right? So if the source voltage or the gate voltage are not dependent on RA and RB, which means there is no loading effect, which means this is all good. Okay. So if that is the case, what is the incremental current? What will be the incremental current through the transistor? Because ultimately we are interested in this voltage, incremental voltage V naught, right? So that will be the voltage for a differential amplifier, right? So what is that voltage? Calculate and tell me. You can still assume GM1 and GM2 are slightly different. In generally, can you calculate and tell me what will be V naught in terms of VA and VB? Okay, tell me, what are you going to get? Yeah, this sounds right. So you are going to get this expression where this guy becomes your, or I can simply write it in the other way, right? I can write it as GM1, GM2 RL by GM1 plus GM2 times VB minus VA, where this becomes the gain of the differential amplifier, right? So in other words, what I'm saying is your V0 over VB minus VA is GM1, GM2 RL by GM1 plus GM2, right? So this is the gain of this structure. Okay, so this can be used as a differential amplifier now, because in that feedback loop, in this feedback loop, I can attach the plus terminal and the minus terminal wherever I want with respect to the structure that we just used, because none of these terminals are going to load the previous way. Okay. So let me just write out the entire thing here. Okay. So this is so far so good, but now next question will be that this is incremental. We need to figure out the biasing conditions also, right? So if we have to figure out the biasing condition, we'll have to then replace this incremental equivalence with the transistor equivalent and then put current sources or voltage sources wherever is necessary. So the first thing obviously is to replace the incremental equivalence with the transistor equivalent. So that is easy to do. So let's do that. So obviously the gates have to be biased with some voltages, right? Other than without the voltage, there is no point without biasing voltages. So this will also be biased. Let's call this capital VA, capital VB. Okay. So let's concentrate on the drain. So the transistor on M2 was a common drain amplifier, right? So the drain was connected to VDD, so this was not a problem. M1 was kind of acting like a common source amplifier, right? Because we were trying, it's not a common source amplifier, but we are trying to drive the source of M1 through M2 while the resistor was connected at the drain, right? And incrementally shorted on the other side. In other words, the resistor was connected to VDD. This is all good. Then we also started off, how were we biasing this M1 with the current source at the source, right? So this M1 was getting biased with the current source at the source. And now the question comes, how should I bias M2? Because M2 was a common drain amplifier, right? We can bias common drain amplifier with again a current source at the source, right? Okay, so we can do this. Let's call this I0. Also, let me call it I1, I2 because we are also using that suffix I1, I2. Okay, so now the question is, how should I connect these two terminals? The sources of M1 and M2. Should I connect? I mean, what is the generic strategy? What should I do? So if M1 and M2 are not identical, and if I1 and I2 are not identical, generic cases, right? If it's generic, then what should I do? What we have done all throughout the course is to find out what is the DC voltage at this node, find out what is the DC voltage at this node. If there is a difference of DC voltages, you put a battery of that difference and connect. And then we say battery is not possible, replace the battery with the infinite capacitor, right? So we can simply put an infinite capacitor here. Okay. So now this will work definitely. But in most cases, M1 and M2 are identical. In most cases, because we wanted the differential amplifier to be symmetric for its transfer function from either of its terminals, right? So we wanted M1 and M2 to be identical. So if M1 and M2 are identical, then let me say their bias currents are also I0 and I0, right? So these currents is also I0, this is also I0. Their GMs are also same. Let me call them GMs and GMs, which means what can you comment on the source voltages of M1 and M2? They are same. If they are same, I can simply connect them without the issue of loading, right? So I can simply connect them, right? So if I simply connect them, these two current sources come in parallel. So why use two current sources? I can use a single current source of value 2I0. Okay, so this is the structure of a classical differential amplifier. I'm sure you all have seen in your UG textbooks multiple times. But the essential genesis of this differential amplifier is that of a common source amplifier whose source cannot be loaded with another terminal, right? So essentially, this is like a common source amplifier whose source is driven by a common drain amplifier. Okay, and it is not a surprise that the transfer function of this is similar to that of a common source amplifier, right? The transfer function is what? Is this AV is equal to, I can say that this GM1, GM2 by GM1 plus GM2 is equal to some GM times some RL, right? Where GM is GM1 times GM2 by GM1 plus GM2, right? And if GM1 and GM2 are identical, if GM1 and GM2 are identical, then V0 becomes minus GM by 2, VA minus VB. Okay, times RL, obviously, times RL. Okay, so So this again is like a transfer function of a common source amplifier with a different value of GM. This is equivalent to saying that if I had a common source amplifier where I connected a VA here and VB here, right? And we had RL here, and let's say the transistor has a transconductance of GM by 2. The transfer function that I would have gotten is minus GM, in this case, GM over 2 times VA minus VB negative of that times RL, right? This is exactly what you are going to get in a differential amplifier, because a differential amplifier is nothing but a common source amplifier in disguise, right? The only difference is it prevents the effect of loading. Okay, so sometimes we treat different circuits in a completely different manner. It's not usually the case. Often, an evolved circuit is a circuit with multiple transistors is an evolution of a single transistor circuit, which is trying to achieve some other functionality. Right. So in this case, as you see, it is a differential amplifier again is like a common source amplifier with a different value of GM. Okay, and the functionality that we are trying to achieve in this case is to use two input sources and to ensure that the structure is not loading either of those sources. Okay. Okay. Any questions?
How do we know this is common source?
Ideally this is not a common source amplifier, but what I'm saying is this transfer function is quite similar to that of a common source amplifier. And the reason it is quite similar to that of a common source amplifier is because we developed it from a common source amplifier, right? So it is only the transfer function that is similar, but the loading is not similar, right? So in a common source amplifier, the source is loading source of the transistor is loading the voltage source. In this case, in a differential amplifier, the key difference between the differential amplifier and common source amplifier is the loading is absent. But as far as if you show this expression to anybody, they might conclude that it is equivalent to a common source amplifier where VA has been connected to the gate and VB has been connected to the source. And the common source amplifier has a transconductance of GM by 2. Right? What I'm trying to motivate here is that this is not, as far as the circuit development is concerned, it is exactly the similar. It's exactly similar. The only difference is that there is a buffer connected to it. Okay. Okay, fine. Any questions? Okay, so in the next class, we'll start from here and we'll develop, we'll get into analysis of common source differential amplifier in more detail.